So no questions? They're all good? All of them. So we started by definition of moments, right? And as I said, when it comes to the rotational action of the force, you either want to consider the force in 3D space. The force may be trying to rotate a 3D object, okay? And it may rotate that, or your interest is about to find out the action of this force on this object about certain point O, or the rotation of this object about certain axis. So in 3D, you are interested in finding a moment either about a point or about an axis. I will demonstrate both concepts through examples, okay? We've seen already moment about a point. As we described that, definition was that moment of a force about a point can be obtained by connecting that point about any point along that force, which we call that position vector, and you can find that action or rotational action by forming this cross product, which was basically to determine the outcome of this operation, which is determined, f of x, fy, and f of z. So let's first do a problem on that, and then we will talk about moment about an axis. I have a good problem that I have selected here, so I'm going to start with that. Okay. So let's say you have a panel that is supported along these two edges, along x, y, okay? And I would label that as A, B, C. The coordinates of these points are given. This edge is 2.5 meters long. This edge is 2 meters. You have attached a cable to point B that is connecting that board through that cable to a point on this plane, and that point is labeled as D. Coordinates of that point are given. This is 1.5 meters, and this coordinate is 2 meters. Okay? You know that the force that is acting along this point, along this force, which I call that force T, or tension force T, BD, magnitude of that force is given as 900 Newton. So this is what's given. What you want to find is if this point is O, what is the rotation that this force causes about point O, or the moment of this force T, BD about point O. That's what you want to find, okay? Remember, we said moment of a force about a point can be obtained from this cross product. How do you determine what is the position vector? You just connect that point to any point along the force. Obviously, you're only given coordinates of 2 points along this force, so you need to connect that point to either this point, you have two options, or this point. Either of these two can be used as the position vector, doesn't matter. I choose OD, so I would write OD cross T of BD. So as the first step, step one, in all these problems, what do? Write the coordinates of all points, important points that you have, so you can keep track of what you need to find out in the problem. So point B is given 2.5, 2, 0. Okay? Point D has the coordinates of 1.5, 0, 2. And that's all you need. And of course, point O, which is 0, 0, 0. So step number 2, you write the equation for the moment, the vector equation that you're looking for, you want to find, which is moment of that force T, BD, about point O, which we know by now is what? OD cross T. So, therefore, you need to find the vector equation for the position vector. You have the coordinates of D, so you have tip minus tail, 1.5 minus 0, I, 0 minus 0, J, 2 minus 0, K. So this is the position vector. What is the equation, vector equation for the force? Would be the magnitude of the force times the unit vector along the direction of the force. So would be 900. What is the unit vector? Tip minus tail. So this is the unit vector. Always consider the unit vector along the same direction as you have chosen the direction of the force is. So this would be the D minus B. So it would be 1.5 minus 2.5 minus 1 I, 0 minus 2 minus 2 J, 2 minus 0 K, divided by the length of BD, which is 1 squared, or negative 1 squared, plus negative 2 squared, plus 2 squared, so that is square root of 9, so this would be 3. So the outcome, or force of BD then, will be negative 300 I, negative 600 J, plus 600 K. Okay, so this is the position vector, that is the force. So the moment of TBD about point O will be, set up the determinant, I, J, K. The second row is the position vector, 1.5, 0, 2. The third row, components of the force, negative 300, negative 600, positive 600. Expand this determinant according to the first row. So this is positive, this is negative, this is positive. The outcome would be eliminate row and column corresponding to I. So it would be 0 times 600 minus 600 times 2, so 1200 I. Eliminate this row and column corresponding to J. Sign associated with J is always negative, so it would be 1.5 times 600 is 900, minus 2 times minus 300, so positive 600 J. So this is 1500. Then for K, eliminate this column and row corresponding to K. So you have 1.5 times 600, 900, and then 0, so 900K. So this would be the moment that results. 1200I minus 1500J plus 900K. So this is the moment that that force generates about point O. Obviously, this is a vector, right? Moment of TBD about point O. Magnitude of that moment would be what? The square root of some of these squared. Okay? So if you write that, you see this comes out to be 2,142 Newton meter. Okay. So to visualize this, this is the vector. What that means, okay? If this is x, this is y, this is z. This is the x component of that vector. To differentiate between a force and a moment in terms of representing them vectorially, we use a double-headed arrow. If this is positive, obviously this arrow would be going toward the positive direction of x, which means the rotation is going to take place in the direction, the positive direction of x. So, in other words, that force will rotate that platform about x-axis, tries to rotate it in this direction. About y-axis is going to rotate it in this direction, because it's in the negative direction. So in other words, it's going to rotate the object in this direction. So this is 1200, this is 1500, and for J, it's going to rotate in this much, in this direction. Yes?
In the K direction of the moment, would it be negative 900?
Is it negative 900?
Yeah.
K would be 1.5 times, yes, that is negative. Good that you noticed, yes. It is negative, so it's going to rotate then in this direction. So 900 Newton meter, okay? You can, of course, if you want, you can draw the actual vector or the moment in space would be something like this, I don't know. Maybe something like this. How do you find the angle that this vector makes with the x-axis, theta x, theta y, and theta z, like any other vector? Cosine of theta x, for instance, would be m of x divided by the magnitude of that moment. So it would be, for instance, in this case, 1200 divided by 2142. So that will give you theta x, if you want to find that. Same thing, theta y, theta z. But when you're giving, or you're expressing the vector, in this case a moment, in vectorial form, implicitly you know what the direction is, because you basically know the components. Okay. Any questions? So that's a good example of moment about a point. No question? All right, so I'll do a problem for moment about an axis, okay? I have prepared a good problem here. Moment about an axis. What is a moment about an axis and what is the application? Okay. Let's say you have an object. This door is a good example. This, you want to, say, design some rotational springs that when you exert a force like this, they would automatically shut this door, right? So these rotational springs will be subjected to a moment that is generated due to the action of this force that will rotate this door about those rotational springs along this direction. That's one example. Another example, I always give this example, goes back to the old days, right? In the old days, cars is a typical 1974 Ford Falcon. You don't even know what Ford Falcon is. Okay? They don't make them anymore. So in the old days, when you open up the hood of a car, you want to hold it in place, okay? You had a little rod here that you would lift it, put it in a slot here, and would keep the hood in place. You have basically a couple of rotational springs here, and you want to hold this hood in place. You know what force this rod is exerting on this hood, so you want to design these hinges, rotational springs, such that they would basically keep this hood in place. So you need to know what is the rotational action of this force about this axis. That's the meaning of moment about an axis, or that's the application of moment about an axis, okay? So this is physically what it means. So mathematically, what you're trying to find is what? You have a force, F, and you're given an axis, D, and you want to basically find the projection of the moment that this force is making about the point of this axis, about this axis, along this axis. Or in other words, the meaning of the moment of a force about an axis is moment of that force about an arbitrary point along that axis, which is obviously a vector, dot product of that, and the unit vector of that axis. That's how you find the moment of the force about an axis. And all we care about is what is the magnitude of this moment about this axis. So to find that, first you need to choose an arbitrary point along that axis. Find the moment of that force about that arbitrary point. What does that mean? You connect that to any point along that force. So this is what? R cross F. You find that vector, which is the moment of that force about this point. Once you find that, okay, you find the unit vector of this axis, and then find the dot product of these two. And what is the dot product of two vectors? Sum of the products of the corresponding coordinates versus x component of this vector times x component of this vector plus y component of this and y component of this plus Z component of this multiplied by Z component of that. So let's just demonstrate that through a simple example. Let's say you have a rod here or something that is connected to this point A through some maybe hinge. Length of this rod is given 6 meter A, B. And a cable is connected to point B, which attaches that to this wall at a point C, and the coordinates of this point C are given. 0, 2.4, and -4. In other words, we know the distance from the X, Y, and Z axis of that point, okay? The force in this cable is given. Force in this cable is given as 2.5. So the force in this cable BC is given 2.5 kilonewton. Okay. We want to replace this connection with a different type of connection by, let's say, welding maybe a piece of, if this is a metal rod, you want to weld a metal piece here and then put 2 hinges here instead to support this rod instead of through this pin here. So you have some rotational springs that you want to design. Therefore, you want to find the moment of this force BC about this axis ED. That's what you want to find. Okay. Any questions as far as, yes?
Wait, so which way is it rotating?
Apparently if the force is acting this way, this rod is going to rotate about this ED like this, right? And you want to find the magnitude of that moment that is generated about ED. Okay. Coordinates of E and D are given. Coordinates of E, okay, let's see, is 0, 1, -1.5. D is 0, -2, and 4. So coordinates are given. So this is how you attack any moment about an axis problem. These are, again, the steps involved. Okay? Step 1, as I said before, in any 3D problem is what? What is step 1? Write the coordinates of all the points that you need. So step 1, easy. Step 1, write the coordinates. So B is what? 6, 0, 0. C is given. E and D are given. And A, obviously 0, 0, 0. So you have the coordinates of all these points. Okay. Step 2, write the equation or the quantity for the equation, that you want to find its value, right? Here, what we want is we want to find the moment of this force, BC, about ED. Okay? So based on that, you determine what? If you write this equation, moment of this force about ED is what? You need to find the moment of this force about a point along this axis, okay? So when you need to find a moment of that force about a point along that axis, what do? As an engineer, always find the easy way out. We engineers are lazy, right? We want to find the easy way out. So which would be the easiest point? A, right? So I will consider moment about A. Then you need to find a dot product of that and the unit vector of ED. Okay?
So there are we choosing between like A or B, or like A
Or actually any point along this line. So it would be E, A, or D. And we'll see why A is the best in more details. So as the next step then, step 3, what do you need to do? Find the moment of this force about A. Why did we choose A? Because moment of the force about point A, right, is what? A position vector now, right, that connects A to any point along this force. What point would be the best to choose? What, no, what point? B, yes, you got 2 points. Send me an email. Why? Because you have this choice. Either this position vector or this position vector, right? Which one is again the easiest? This, because that has only one component. So I choose R being AB, okay, cross that force BC. So R of AB, the equation for that is simply 6I. Force in BC is what? Magnitude of the force, 2.5 kilonewton, times the unit vector of BC. So it would be 2.5 times, what is the unit vector of BC? Tip minus tail. 0 minus 6, so minus 6I. 2.4 minus 0 plus 2.4J. Negative 4 minus 0, so negative 4K divided by negative 6 squared plus 2.4 squared plus negative 4 squared square root of that. If you simplify that, you'll see that T of BC comes out to be, I have the answer here, 2.5 times negative 0.8I, negative point, no, positive, that's okay, 2 point, the positive 0.32 J and negative 0.5 A K. So that would be the force. So to find now the moment of this force BC about A, that would be simply this determinant. I, J, K. Second row is the position vector. So 6, 0, 0. Third row is that, 2.5, negative 0.8, 0.32, negative 0.58. Again, if you expand it according to the first row, that will be simplified, and you will get this very nice vector that would be negative 0.48, negative 0.48 J plus 0.88 K kilonewton, that would be kilonewton meter. Okay, that's the moment of this force about point A. So that's step 3. Last step, now you need to find the moment of this force BC about ED. So you need to find the dot product of this, or in other words, dot product of 0.48 J plus 0.88 K and the unit vector of ED. But what is the unit vector of ED? Tip minus toe, minus tail. 0 minus 0, 0 I, minus 2 minus 1, so negative 3J, 4 minus 1.5, so it would be plus 5.5 K divided by 3 squared plus 5.5 squared square root of that. If you simplify that, I have the result here, a unit vector would be negative 0.48. I don't want to even write that down. What you need to do, oh, actually, that I wrote this one wrong. That one was not that, so I have to correct that. I was writing it wrong. This is not that. This is 8J and plus 4.8 K. This comes out to be unit vector would be negative 0.48 J plus 0.88 K. Okay. Now, what is the outcome of this operation? You need to multiply I times I, both of them are 0, J times J, so this would be 8 times negative 0.48 plus K times K, so it would be plus 4.8 times 0.88. Sum of these two would be 0.384 kilonewton meter. So this results in 0.384 kilonewton meter. So that is the moment which that force generates about axis ED. Okay? Any questions? Great. That means you're all set, right? Okay, so let me go now do a 2D case. You sure no questions? Easy, right? Okay. All right. So now let's get to the case of 2D moment. Okay, so as I said, again, let me summarize. We are talking about moment. We studied 3D, case, now we're going to do the 2D. So we looked at moment about the point in a space and about an axis. Now we want to look at a special case, which is a moment in 2D. Right? Let's just start with the definition of a moment of a force about a point. In the case of 2D, both the object, which is a two-dimensional object, the point of rotation reside in the same plane. So the problem that we have in hand is you have a point, a force applied on this object, you want to find a moment of that force about this point. What is the general concept? You connect that point to any point along this force, you call that position vector, and according to the definition, moment would be R cross F, right? From the definition of vector product, we know the magnitude of this cross product is the magnitude of R times the magnitude of F times the sine of the angle that is made between the position vector and the force. But what is R times sine theta? If you look at here, draw a line from A perpendicular to the direction of the force. In this triangle, this vertical distance, which we just drew this line that shows that, okay, is the vertical distance from the point of rotation to the direction of the force, right? In this triangle, it is this side, which is R times sine theta. Therefore, the magnitude of that moment about point A would be simply magnitude of that distance times the magnitude of the force. So in the case of 2D, magnitude of the moment about the point is simply the magnitude of the force times the vertical distance from that point to the direction of the force. Since all of these are in the xy plane, the vector that results, or the moment, is perpendicular to this plane. So it's either in the positive direction of z or in the negative direction of z. In other words, it's going to rotate the object either this way or this way. So in the case of 2D, the moment that we're dealing with, we know already its magnitude, very easily obtained, right? So all we need to know or find out is a direction. If the direction is acting counterclockwise, in the negative direction of z, we call that positive. If it is acting clockwise, we consider that to be negative. Since if you have several forces, you want to find some of their moment about a certain point, they are just algebraic values. So you just evaluate each one this way and add them up. Okay? So let's demonstrate that through, again, a simple problem. And in fact, as I present that problem, I will introduce also a very important concept that makes your life a whole lot easier when you're dealing with moment of forces in 2D, or two-dimensional case. The problem that I've selected is problem 3.8 in your book. It's a good problem because it is a good way of demonstrating a few concepts. This is the problem. You have a crowbar, okay, that you're using to try to pull out a nail here. So you apply a force of P acting at an angle alpha with respect to the line of horizon, and you try to pull that nail out. This tip of this crowbar is residing at point B along that piece of timber. The problem has three parts to it. First of all, the length in this part of this crowbar is 18 inches, and we know this angle is 70 degrees. You also have been given the distance between this point and point C as 4 inches. Problem has three parts. In part A, as the problem states, a force of 200 pounds is required to pull this nail out of this piece of timber. So in other words, in part A, the problem states that a force of 200 pounds is required to pull this nail out, okay? And the problem is asking, what is the moment that this force of 200 generates about point B? So this is basically part A. What is the moment of this 200 pounds about point B? Okay. Moment of a force in 2D with respect to a point is simply the magnitude times the vertical distance from that point to the line of action of the force. And this is the vertical distance, which has already been given, 4 inches. In 2D, as I said, the only thing that you need to worry about is the direction of the moment. The easiest way to find the direction of the moment, always think of it this way, that you have connected that point to anywhere along the line of action of this force, versus this line, and assume that this is a rigid link, pinned here, and you want to move your force along the direction that is applied. What direction this linkage will rotate? Obviously that way, right? That is the direction of the moment that is generated. So in this case, the moment that would be generated, its magnitude is 200 times 4, but will be clockwise, or like this. So it would be 800 pound inch clockwise or negative. Either one is the same. Okay? Any questions? In part B of the problem, okay, it states that if that alpha is given as 10 degrees, how much should be the magnitude of the applied force that would generate the same moment about point B? In other words, we know the moment of this force P with this given orientation, this being 10 degrees, okay, is the same 800 pound inch. So you want to find the force that would generate that moment about point B, given the direction of the force is given, okay? I will introduce a concept which is based on general concept developed by Saint Varignon. You may have come across this name somewhere in matrix analysis or someplace. Vectors. Varignon was actually a clergyman. And back in those days, clergymen actually did some useful work. They were not just sitting in the church all day long and reading Bible. They were doing other things. So this guy was actually a mathematician. So he came up with this good idea. Implication of that idea is as follows. That the moment of a force about a point is the sum of the moments of its components about that point. This is, of course, he wasn't talking about moments, but that was general. But the implication in the case of moment as a vector is the simple finding. What does that mean? You want to find a moment of this force about point B, which means you want to find, you have to find this vertical distance from this point to the line of action of point B. That's not easy. It involves at least a little bit of geometry. But he said, if I use Mr. Varignon's theorem, what I would do, I would resolve this force into its components first. So I find Px, which would be P cosine of 10 degrees, and P sine of 10 degrees. So moment of P about B would be moment of Px about B plus moment of Py about B, right? What is the moment of this force about B? Is it positive or negative? Again, think of it. Connecting these two through this rigid bar, this moves that way, this rigid bar moves clockwise. So that would be, yes, negative. Whereas this one is trying to move this, rotated in this direction. That would be positive. How do you find out these two values? You do have the distance from B to Px. In this triangle, right? That is 18 sine of 70. And you do have the distance from here to this. In that triangle, that's 18 cosine of 70. So you just write those down. So you have P cosine 10 times 18 sine 70, obviously negative, plus P sine 10 times 18 cosine of 70, and add them up. These should be equal to 800, or negative actually 800 pound-inch, okay? So from here, you find P that comes out to be 51.3 pounds. This concept of St. Varignon, remember that? Because we will be using that throughout the entire course from now on. Always think about it. When you have a force, resolve it into its component, find the moment of the components, add them up. That's a whole lot easier than dealing with a force in the general direction. Okay? So you have all the ammunition you need to solve your homework problem.